Okay, this must be better. Hey everyone, I'm Gabriel, and I will be presenting on our work on dafny-annotator. This is joint work with Chloe and Professor Nada at Harvard, and I'm a PhD student at Stanford. Okay, so I think we all know that bugs cost a lot of money, and it seems like they cost a really surprising amount of money if you've seen these reports on the cost of software quality. There are some estimates of like 1.5 trillion in 2020, for example, in the US. But in principle, we have this amazing thing called software verification, which could prune a lot of this, the cost of bugs, right? So why is it not the case that everyone is using it yet? And unfortunately, it might be the case that we're still at the stage where the cost of verifying significant software to the level where we would not see those failures appearing might be higher than actually just waiting for the bugs to happen and fix them, which is unfortunate. We don't want that to be the case. So then we have to think about, okay, so what are ways in which we can lower the cost of formal verification? And there are, I think, for sure more aspects here of developing verified software that are not covered here, but at least two of the obvious targets that we have are the cost of specifying formally. Usually people don't think about this or are not even trained to think about what their code actually does. So if this is a square root implementation that someone might write, that looks like normal code. But for a regular programmer, now that I have to write a logical formula that says what this does or what I intended to do, that is an additional cost. But just stating what we want the program to do is not usually enough. We usually also need to provide the verifier with some artifact, some proof, or in Dafny less than that, maybe some invariants and assertions would be enough. And Dafny really tries to shine in this second stage for using Z3, as we've seen, instead of rely on users to interactively develop proofs. But oftentimes, even when we insert some logical annotations in a program, Z3 doesn't seem convinced. And it's often unclear, as many of the talks refer to, if it is that we just have a bug, or if Z3 is just not yet powerful enough, or maybe the version changed, and if I had done this last month, it would have worked. So in this talk, we're just going to focus on one particular scenario here, which is the second case of convincing Z3, which is true. We assume that we have a function that is already correct, which was not the case here. So that's another problem. Maybe Z3 is unconvinced because you actually have a bug. We're assuming that you have no bugs. You wrote you have a method in this case. We're not actually dealing with functions. That is correct, but has no annotations. And Z3 cannot automatically prove its correctness, according to the specification that was written. And we're going to ask whether language models can help a user in this scenario, where they wrote regular code, and they actually wrote their specification of what they want the code to do, but the verifier is still not convinced. OK, so this leads to this tool called the Dafny-annotator, which will basically work as this diagram shows. You have a program that's already written there, and then an LLM will try to incrementally add annotations until hopefully Z3 is convinced. So we basically repeat this process of giving the language model the program that we have so far, and then ask it to output one annotation that it would add to this program. It might be an invariant, treasure loop, a decreases clause, for example, to prove termination, or an assertion, or anything. OK, so we'll repeat this very simple greedy annotation algorithm while the method with timeout, or the method still not fully verified. We'll use the LLM to propose a set of candidate annotations to add to this method. We'll attempt in parallel to insert these annotations at each of the syntactically valid positions to lower the burden on the language model to actually localize where to do this. And then if Dafny accepts that annotation anywhere, we'll add it there and repeat. And repeat this until until either we verify the method or we time out. In our particular experience, we use 5 and 5, 5 iterations and 5 candidates each time. And OK, so this is a super simple, straightforward system that we could try to build on top of current LLMs, right? And then we can ask, OK, so how well does that alone work? So we evaluated this using two base models, LLaMa 3.1, 8b, and LLaMa 7b. So these are relatively small models that you can run on not huge GPUs at this stage. And we evaluated them on verifying programs from DafnyBench, which will be, I think, maybe the next talk. So that will be. But as far as I know, DafnyBench is the largest existing collection of Daphne programs that was collected from GitHub after some filtering and making sure that they compile and run standalone and so on. So what we did is we held out 20% of DafnyBench for testing, and we'll also evaluate whether training the model in the relatively few number of programs that we have helps. And so for those test problems, we stripped all of the annotations, and we filtered out the programs that verify even without the annotations, which turned out to be most of them in this case. I think in DafnyBench, it's more than half. I think like maybe 60% don't need any annotations. But a lot of the problems come from, for example, problem sets and classes, so the annotations are more kind of illustrative rather than actually required. Yes, so OK, so the one small detail that appears here is now that we have some training data, possibly, and we'll see how that affects the model, how do we train the model to use those programs? So language models are trained to predict the next token, given some tokens that exist so far. So the most straightforward thing you could do is to just train them on the programs that would reinforce that those are the tokens that it should generate in sequence. But that's not actually very helpful for this task, because here we have this format where we have a partial program, and we want the model to output one annotation to add to this program. So what we do is basically we strip all the annotations from the training programs when we do that, and then simulate this process of adding back the annotations one by one and asking them, making a training example that is like, if you have this program, this is the annotation you should predict, which is the next one that comes in the program. And then we add that, and then if the program still doesn't verify, there's another annotation that comes from the human program and so on. And we have that process. OK, so unfortunately, large language models have this large in their name, which usually means that both the models are large, but also their training data is also quite large. And it's hard and kind of unstable to do fine-tuning with small data sets, which turns out to be the case even for DafnyBench. So if you have LLaMa 3.1, just the base model can verify 15% or around 16% of these held out programs. If we fine-tune on some proportions of DafnyBench, we see this kind of unstable behavior of like, if you fine-tune on everything, there are a lot of actually low-quality programs in DafnyBench. It doesn't seem to help the model. But there are some subsets of DafnyBench that actually give it a little boost, up to 20%. LLaMa, which is a similar-sized model from a previous generation, actually benefits quite a bit more from fine-tuning. So it goes up to 40%. But OK, so usually one of the so OK, we get those numbers, that's fine. But usually that's not 100%, and we would like it to be 100% in the ideal case. And there's always a question when you have a black box component in your system that's like a language model. It begs the question of how can you improve this system, right? If it depends on this weird agent there that's making predictions that you can't really control. So it seems like fine-tuning generally helps language models. But if we want to rely on this recipe on fine-tuning them more and more data, then we need data. And unfortunately, there's not that much data on Daphne out there. DafnyBench is kind of already most of the examples that we could use to fine-tune the model for this task. So what do we do? Maybe we just wait a couple of decades and wait for people to write a lot more programs, and then our language models will be great. That's one way. But if we want to speed that process up, there's another idea, another set of ideas that have been explored in language model space these days, which is to generate synthetic data. OK, so this introduces this method and dataset that are called DafnySynth, which is a little bit of a wild idea, I would say. So the idea here is that all we want to make the system better is more examples of Dafny programs with annotations that are actually required to verify the program. It doesn't actually matter what these programs are or where they come from. So the high-level idea that we pursue here is to just set up an open-ended generation, open-ended system to generate Dafny programs. We'll see exactly how that works, but the basic idea is that we'll try to combine this generative model, which is the language model in this case, which can give us whatever we want it to give. It's not very reliable. With a verifier that can actually give us some stronger signal. In principle, these two components together could give us an unbounded number of verified good Dafny programs that we could use to train and then improve the system. So the idea is that we incrementally generate this set of programs, and the verifier will let us filter logical annotations and specifications that don't match, basically. And then after we do this and we collect a large number of programs, all of these examples can serve as training examples to fine-tune our model. And then we can see if that helps at all. So the idea of DafnySynth is this generation pipeline that is basically growing a graph where each of the nodes has some content. There is a root node that's just there to kickstart the process, doesn't have anything in it. But then from this root node, or by using language model, we'll propose high-level ideas of possible programs we could write in Dafny, in natural language. So that will give these nodes in this graph, which we'll call the idea nodes, which will just be text in them. And then given an idea node, we'll have an editor that will, one component we'll call the implementer, which will take this idea node and try to write not a very ambitious, like just a small Dafny program that's kind of going in that direction of what the idea is describing. So this gives a program node. Given a program node, we'll have editors that will then try to make this program more complex, like implement new features, maybe edit some of it, or maybe re-implement what is there in a different way, and so on. So this will be basically these editors. So proposer will create idea nodes. Implementer will take an idea node and try to write a program, which we can check if it's valid with Dafny. The editor takes a program, proposes a patch, so that will be applied, gives a new program. And we also have we found that it's better to try to keep programs that are syntactically valid but don't verify yet, and then let this annotator try to then annotate them, and sometimes you are able to eventually get a verified program. So in principle, we could put money as much as we want and get programs on the other side, and then see if that's good training data. So this gives a graph that would look a little bit like this. And just as a concrete example, so from the proposer using GPT-4o, we'll sample, if sampling a bunch of ideas, one idea that we'll come up with is a program that verifies a priority queue and ensures that the elements, that the order of the elements is correct based on priority. So that's one of the ideas that will come out. I could not find actually this on DafnyBench. Like if you grab for a bunch of these keywords, I did not find a priority queue in the existing programs. But GPT-4 will actually start to implement a priority queue, and after a few edits, you'll get a few, 150 lines of code of a class that implements a priority queue, has a bunch of annotations and so on. So I think this can go surprisingly far, even this very basic idea.
Was the priority queue itself suggested by GPT?
Yes. So of course, it has tons of programs that people wrote in other languages, right? But the useful thing here is that we don't have this one in Dafny, so that's already a win. So in DafnySynth, we use GPT-4o version from many months ago to implement all of these editors and spend $10 of OpenAI API credits. And $10 gives us a similarly sized data set to DafnyBench, which is the programs that are collected from GitHub. So it's not a lot of money, and it's already quite a bit of data. And then the question, of course, is this useful training data? And maybe surprisingly, the answer is yes. So if we just augment the existing training set of DafnyBench with DafnySynth, we get one of the base LLaMa 8 model to verify 50% of the programs, or a tiny bit beyond that. Yes, code LLaMa doesn't actually seem to benefit too much from the synthetic programs. But yeah, this could just be some instability of training as well. But yeah, so just to summarize, I think it's plausible that at this age, LLMs can help end users use tools like Dafny, for example, lowering the cost of verification. Maybe also for specification, though they might also misspecify things, especially for people that don't have the experience doing it by hand or don't understand the system very well. So they might get a program that was proved correct, but for the wrong definition of what correct means. And of course, there's a lot of ideas we could do in this editing pipeline that we don't yet do. So for example, right now it spends a lot of money trying to implement ideas that are completely crazy. And we kind of just randomly sample ideas and so on. Something like MCTS, for example, could very naturally, over time, focus on ideas that seem to be more promising, that seems to be able to keep growing, and so on. We could also just use programs from other languages so that it doesn't have to start from scratch, but maybe here's a Python program, write something that's a bit like this, possible specifications, and so on. And yeah, so I guess maybe the main takeaway here is that there is one possible path to creating good AI assistants, even for languages that haven't had yet large-scale adoption. And that might have this positive feedback loop of a language that has very good assistants might have more people using it and so on. So yeah, that's it. Happy to take questions.
Wonderful talk, great ideas. So you've measured the usefulness of the generated DafnySynth data by how well it helps to fine-tune the models.
Right.
Can you say something about like a human evaluation of the dataset? I mean, are these good Dafny programs? Are these like reasonable specifications, or are these like smileys?
Yes, that's a good question. I think they're a mix. I found very few like completely bogus programs, if at all. I did find a lot of trivial programs and specifications. Like in implementing, for example, a voting system, it would ensure that the new vote is the old vote plus one, and the implementation of the function is new vote equals old vote plus one. Things like that. So you get a lot of that. In these more complex programs, usually, like in the priority queue example, oops, this one. Usually the specifications make sense, and it fails to like fully verify some of the methods. But I think even the existing annotations, like the invariants that it writes, for example, tend to be sensible. But yeah, I think it's hard to think about like what would be the direct usefulness of this for humans to do a human evaluation. But it would be useful, cool to think about too.
Thank you.
Yeah.
So you mentioned that you use GPT-4o
Right.
to generate this synthetic dataset, but then you fine-tune another model, right? Called LLaMa. So have you? There is a little bit of a problem with that, right? It's kind of a poor man's technique to steal the weights of some model. Is you just query it for 1 million inputs, and then you train your own model on what you got, and then you have kind of maybe you've stolen the training. So to what effect, or do you have any way to kind of measure that effect? Or maybe put it in a different way, if you just use GPT-4o initially instead of this code LLaMa, would you get better results compared to after you did with the fine-tuning with the synthetic dataset?
Yes. So we did a preliminary evaluation of 4o early on in this test set, and it did not get 50%. So I think, I forgot exactly. I think it was around what code LLaMa got after fine-tuning, like 40. So even this process of synthesizing the data using 4o, combined with the information that comes from Dafny to like filter bad programs and so on, and then fine-tuning seems to do better than 4o alone.
And did you try to just use code LLaMa or LLaMa for the synthesis instead of GPT-4o? I mean, what made you use
Yeah, right.
GPT-4o?
So I did, not super seriously, but I did. And it seems like this open-ended generation for the small models is really hard. Most of they don't generate anything like that's this long and still coherent, for example. Like they try to start to repeat themselves and things like that.
I guess let me try to pose two hypotheses and ask your intuition about which is responsible for what. When you're doing this process, one source of information is GPT-4o that was maybe trained on much more Dafny code than DafnyBench, and we don't know. And maybe it's very smart.
Mm-hmm.
And the other is that there is feedback from the verifier here.
Yes.
Right? You're using the verifier to get actually good Dafny programs.
Mm-hmm.
And I guess the question is, which one is responsible for more of the effect? Are you just stealing the training from GPT-4o?
Yeah, right.
Or is this generation process kind of getting more information because of its use of the verifier?
Right. So I think, it's unfortunate that we can't rule out one. Like maybe OpenAI has a lot more Dafny programs than we know of. But I think that's unlikely, just because it doesn't. Yeah, I guess one question would be like, where would those programs come from? Maybe they would have to crowdsource, like ask people to write more Dafny programs.
Maybe generalizes better from other programs.
Yeah, exactly. So I think that's more likely the case. That like it actually sometimes still makes basic syntactic mistakes in Dafny. So I think it's not really good at the language, but it can sort of get the ideas right. Yeah, so I would say that it's a combination of like having a not too bad, but still imperfect generator, and having the verifier to be able to prune things. So it's likely that like if you were to do a lot more samples on 4o alone, plus using the verifier, you could probably beat the small models even after fine tuning. But then it's also just a matter of cost. Yeah.
Let's thank Gabriel again.